Hello, this is math reasoning video for April 2nd. This video is going to be on functions. Let's get right to it. Okay. So a function, or sometimes called map, is a rule that takes from elements from one of the set, A, called domain, and assigns another element in the range, a single element in there. And the element that it gets assigned to in the range is called the image of the first element under F. Okay. So I'm sure you guys are familiar with this concept, but you might not have seen this notation before. So we use this notation F colon A arrow B to show that this is a function with the domain A and range B. Right, so that is the standard notation that we're going to use from now on. A is called the domain, and B, I mentioned the word range already. It is sometimes also called the target. And sometimes we talk about image of a set rather than image of a single element from the domain. So if you have a set A, and if you set f of that set A, that means all the possible outputs you could get from all of the elements in the set A. And that is sometimes called the image of that set A under the map F. Okay. So this is a rough picture of what you should have in mind. So you could take different elements from domain A, and function is a rule that assigns elements in the range B. All of the points that you could hit with the map is called the image. And it's possible to have some elements in the range where it does not have a corresponding element from the domain to get there. So you don't have to hit every single element in the range. Okay. All right. So here's the homework problem that's kind of in this vein. So maybe I could get you started on this one. So if you have set S and you want to talk about the image of that set S, we can define it this way. Okay. All of the f of x, where x is in the domain. And then let's see, we pick C and D, so some arbitrary subsets of the domain S. Okay, I want to prove that the image of C intersect D is a subset of the image of C intersect image of D. So this is kind of, this proof will involve just kind of unwinding definitions. So let's see how we can get here. So okay. Right, so we will show that f of C intersect D is a subset of f of C intersect f of D by showing we're going to take an arbitrary element in the set f of C intersect D, and then show that it also belongs to f of c intersect f of d. Okay, so that's the general strategy. And basically it comes down to unwinding definitions. Okay, so we'll let element y be part of f of c intersect d. That is equivalent to say, so we're using this definition right here. Okay, if you're in the set f of s, then there's some x such that you get that output. So I could say that then there exists some x in C intersect D such that y is exactly f of x. That's what it means to be in this set. Okay, so then now I want to show that y is in both f of c and f of d at the same time. So then y belongs to f of c because x in c intersect d implies x. So saying that x is in the intersection of c and d is saying that x belongs to c as well as d. So in particular, x belongs to c. But if x belongs to c, then y is in the f of c. Okay. Similarly, y has to belong to f of d because x is part of d as well, because x is in the intersection of c and d. Okay. Now I've shown that y belongs to f of c and y belongs to f of d, so it's in the intersection of those two sets. I hope that made sense. Okay. So I think I'm not going to do part B. So part B of this homework question is showing that you could get a strict subset here. F of C intersect D could be actually smaller, so just a strict subset of F of C intersect F of D. So I want you to try out different functions to see if you can get that counterexample. Okay. All right, so let's say you have a function. There are many different ways to describe a function. So I want to go over these. So by far, what we're most used to is describing a function by a formula. An example could be something like this. So f from real numbers to real number defined by the function f of x is equal to x squared. So these are type of functions we've been dealing with ever since pre-calculus and calculus and so on. It could be, so here's another function, g, defined by adding together two different numbers, x plus y. So this is a summation function. It takes two inputs and then add it together and outputs the sum. Okay. Another way to work with a function is just by having a table of values or listing all possible values. So let's say So, I mean, this is only reasonable to do um, if there's really finitely many inputs that you could have. So if you have a function coming from a set 1 through 5 to a natural numbers, maybe I could just kind of list out all possible outputs by listing all possibilities. So f of 1 is 2 and so on. So it's a little bit less elegant, but you could describe a function this way. Another way you might describe a function by describing it by words or some kind of process in which you could determine the output. So you might say something like f of n is the nth prime number. And if the domain was the same, this describes the exact same function that I described above, right? So the first prime number is 2, the next prime number is 3, and so on. So that might be a slightly more elegant way to describe it if there's a pattern to it. Okay, but you don't, as long as you can describe what the output should be in an unambiguous way, you don't have to have a formula to have a function. Okay, all right. Sometimes when you describe a function by words, though, it might not be clear right off the bat if the function is all the way defined. So sometimes it takes a little bit of convincing to say that function is what's called well-defined. So make sure output is determined for every member of the input. Okay. Sorry, this is kind of flipping out. Okay, so this next definition is a little bit weird. When we talk about a graph of a function, we usually kind of imagine something like that, some kind of graphical object. But in mathematics, when we actually say graph of a function, there's a abstract definition as well. So it is related to the graph that we draw, but this is every ordered pairs x and y, where x is from the domain and y is from the range, and they are related in this way, right? By the input and output of the function. So collection of all those ordered pairs is called the graph. So that's an abstract way to define what a graph is. And reason why you might do something like this is because sometimes you can't, depending on how weird the domain and range is, you might not be able to actually draw it. For example, if you have two-dimensional input and two-dimensional output, like you might have in maybe a function that's defined by complex numbers, then you need four-dimensional drawing, and that's not really possible. So it still might make sense to talk about abstract graph rather than a picture. Okay. Another useful definition is the notion of being bounded. Okay. So we say a set is being bounded if you can find some real number m such that every element inside of the set, the absolute value is less than or equal to that m for all of the x inside of A at once. So it's important to say that this a single number works for every single one, every single element in the domain all at once. If it's impossible to find such a number, then we say the set is unbounded. And the notion of bounded can be applied to function as well. So we say a function itself is bounded if it's a real valued function and the image is bounded. So none of the output, all of the output is less than or equal to some single number m when you take the absolute value. Okay, so let's do a sample proof using this definition. So here's an example problem I took from the end of chapter 1. Okay, sorry. It's a little bit long, so I'm gonna scale it. Okay, so let's say you have two functions, f and g, and they're both real functions. Okay, we want to determine which of the statement below are true. If true, then provide a proof. And if you think it's false, provide a counterexample. So come up with an example where it's not true. So what I want you to do is pause this video and spend, I don't know, a good 10 minutes and see if you can do some of these problems. Please try. Okay. I don't have time to go over all of the solutions here, but maybe I'll do some of these. So problem A and B are similar, and C and D are similar. So I think what I'm gonna do is maybe I will prove part A. So A happens to be a true statement. So if you have two bounded functions, then when you add the functions together, you get a bounded function. And maybe I'll do maybe D. So this happens to be a false statement. So just because the product of the two functions f times g is bounded does not mean both f and g have to be a bounded function. So maybe I'll prove that, and C is also false, but similar proof. Okay. And there's a problem E as well. I think I'll kind of indicate how to attack that problem, but not show the entire proof. Okay, so let's get to it. Let's do part A. All right. So here I want to show if f and g are bounded, then f plus g is also bounded. Let's work on the proof. So this is a proof where we basically use the definition for boundedness 3 times. So we're given that f and g are both bounded. So I have to use the definition for 2 of those functions, f and g. And then using those 2 facts, I need to show that f plus g also satisfies the condition for being bounded. So I end up using this definition 3 times. Let's see how this is done. Okay. So the first step is to write out what it means for f to be bounded. So since f is a bounded function, that means that there exists some real number m such that the output of the function f of x is less than or equal to that same constant m for all input values. In this case, this is a real function, so for all real numbers. G is also bounded, so I can say the same thing, right? Also, G is a bounded function. So there exists another constant, but the constant for function G does not have to be the same as the constant for function f. So I'm going to use a different letter. Let's just say n. There's a constant n such that all of the output for function g is less than or equal to n for all real numbers x. Okay. Now I'm going to use these two functions to come up with a constant for the sum f plus g. Okay. So then, let's see. Well, if we're adding together two functions f and g, if they were, I mean, they don't have to always be positive, but if they're different signs, they could cancel out some. But if they're both positive or if they're both negative, then this will be equal to this thing, the sum of the absolute values. So this inequality is called triangle inequality. It's from the reading of chapter 1. Okay, but I know that this part is less than or equal to m, and I know that this part is less than or equal to n. So m plus n is at least as large as these two things added together. And this is true for all real numbers x. Okay. So absolute value of f plus g is bounded by this constant m plus n for every x real number. And that's what it means for the function f plus g to be bounded. So therefore, f plus g is bounded. Okay. I hope that made sense. Okay. I also promised you I was going to show part D. So part D is about if the product is bounded, then the factors f and g are bounded. So this is a false statement. Maybe I can prove that. So if you want to show that some rule is false, all you have to do is come up with one example, one counter example where it fails. So here we go. Here's a stupid function. F of x equals to 0 and g of x equals to x. Okay. Then the product f times g is equal to 0 for all x. So 0 works as the bound, right? So f times g is bounded, but the function g of x is not bounded because you could always plug in a larger number. So um, so because suppose suppose it's bounded by some constant m, we have that g of n plus 1. If I plug in n plus 1 into the function g, I get n plus 1, which is not less than or equal to m. Right? So that contradicts that it could have a bound. Okay. So that's a counterexample for part D. So you could have functions where the product itself is bounded, but that does not imply that the factors are both bounded. So in this case, f is bounded, but g is not bounded. It is possible to have both unbounded, but this should work for this example. And I'm not going to prove it, but I can kind of give you a hint about part E. So if you have both the product and sum be bounded, then you could show that f and g are bounded. So this is a true statement. What you could do is you could use the quadratic formula for the Babylonian version of the quadratic formula for the first video to show that if you know the product and the sum, then you basically know what the individual function f and g could be. So you could flip f and g, but you know what these functions would have to be. And you want to show that basically the quadratic formula itself is bounded if both the product and the sum is also bounded. So that's the approach there. So try to see if you can finish that argument and see if you can prove part E. I think that would be a good exercise of theorems. Okay. All right. So a few more definitions. Okay, we say that the function is increasing if you plug in a larger input that gives you a larger output. Okay, and we say that the function is non-decreasing if larger input means, well, you might increase, but you might be equal. So you at least don't increase. Sorry, you at least don't decrease. So that's called non-decreasing. This is the definition we'll use for this class, but sometimes different books use different words. Sometimes people call this condition strictly increasing if you're using strict inequality of strictly less than there. And sometimes when it's non-decreasing, people might say that's a weakly increasing. So that includes the possibility of equal sign there as well. Okay, and if you want more practice with proofs, maybe you could try to prove if you have two increasing functions, then the sum of those two functions will also be increasing. So try to see if you can prove that. Okay. Okay. So one more definition. we talked about image of a function. So now what I want to talk about is the inverse image. So if you have a function f and you pick an element or maybe a set, a subset of the range. So let's say y in the output, the inverse image of that output is any possible input that gives that output. Okay. So it's kind of going backwards. When we talk about image, you talk about all the possible outputs you can get from a given input set. If you're talking about inverse image, we're talking about all of the possible inputs that could give you that possible output y. And I gotta say, the notation that the book uses is a little bit unusual. Usually people use this notation f inverse of y to denote the set of all possible inputs that gives you that output. But I do kind of understand why the book chose to make this distinction. So when you write it this way, it makes it look like, oh, this function is invertible and f inverse exists, right? So just by writing that notation, you might look like function has an inverse, but a lot of functions don't have inverses. So I can kind of understand the hesitation the book didn't want to use this notation. But you should know this notation because it is more commonly used than the book's notation here. Okay, so when you talk about inverse images, and if you're talking about a real function, if the output is the real numbers, then sometimes this inverse image is called the level set as well. That might be something that you've heard in maybe like a Calc 3 class. So hopefully that makes sense. Okay, so that's it for this video. I'll see you next time.